Hey, I wanted to do a standalone example of array indexing and addressing in MIPS that you can just use as a standalone resource and reference. This is a more complicated example than you would normally have to deal with. This isn't an example of what exemplary C code may look like as a starting point, but I think it uncovers enough of the issues that you will run into as you try to do this. So let's dive into it, and I think we can cover the ground in a reasonably short period of time here. So in the example I have put together here, we have a number of arrays that we're wanting to access in memory. So we'll start with our int array A. The size of the arrays aren't super relevant for this type of issue. And we're going to have, that's our integer. We're going to have then an array of shorts. We'll call that B, followed by an array of cars, and we'll call that C. And one thing I was showing in the initial examples that we started with in class is it's good to comment this code, both comment the problem itself, as well as to comment the assembly instructions you're creating as a way of documenting, as a way of defending the choices that you're making. Also, just in general, as a way of just stating your assumptions for what is going to go where. Makes your code much easier to understand, much easier to determine if you've done something wrong in a good sense that, okay, I claimed that the address of A, and A itself as an array is a pointer to that first element in memory. I've claimed it's as 0, and that's just an arbitrary place I've decided to put it for the base address. And as a reminder to myself as I'm working on this, that I'm working on my ints here for A, and ints are 4 bytes. Maybe you don't need to constantly remind yourself of that, but for now, in one of our first examples, hey, let's remind ourselves that that's the case. Same with B. So B, let's map that again. B as the name of this array, as we reference it, is the first location in memory for that array. Let's call that S1. Our shorts, and this is really becomes compiler specific, but in our case, for our assumptions, we're assuming that our shorts are going to be 2 bytes. And in general, state your assumptions and you're in pretty firm ground. The C standard is very clear on the size of these data types, but it uses some language that says, our short ints must be, at least this number of bytes. It doesn't guarantee that it's exactly a certain number of bytes. And then for C, that's our single byte data type. We're going to map that to S2, and our cars are just 1 byte each. So that's our setup, and then I'm going to have some just data types to allow us to access those arrays and to index into those arrays. We can say, we can decide where we want to put those later on, but we have an X and an I that are going to be used to access it. So somewhere in our code, and it doesn't matter if it's the next line or if it's 500 lines later, we have X. Our result is going to be set as some index into A, and let's make this a little ugly, which itself is indexing into B, which itself is indexing into C, and now we'll use that I, and let's make it I plus 3 like we had in class. And let's add some more integer offsets to those array accesses. So this is an ugly example. This is arguably an extreme example. Don't sweat it when you run into an example like this, and don't overthink it either. We would work our way from inside out into that, and when we do so, and maybe we just need to relabel things as sort of temporary variables, it's just a straightforward application of the very simple 2 to 3 line examples we've already covered in class that the textbook covers in some level of detail. Another way to think about that is we know we have C of I plus 3, and we have to figure out what C of I plus 3 is to figure out what B of C of I plus 3 plus 4 is going to correspond to. Well, then let's just label this just internally in our own, mind space as, let's call this J, just to call it something that's different. Then this becomes B of J plus 4, and we know how to do that. Just like we know how to do C of I plus 3, we then know how to do B of J plus 4. And likewise, B of J plus 4, let's just assign and call that K. So now then we're calculating A of B of C of I plus 3 plus 4 plus 5, but really it's just A of K plus 5, which we know how to do. And we don't really need to have a shorthand for this final quantity here, a of k plus 5, we can, but that's what's going to correspond to x here, right? That's the actual final result that we're going to want to store back out here. So we have our ints, our shorts, and our chars, our 4 bytes, 2 bytes, and 1 byte quantities here. There's a lot going on here. There's variable indexing and offsets that are constants, but if we just take it from the inside out, figure out what c of I plus 3 is and work our way from there, it's just going to be, multiple examples of doing basically the same exact thing here. So we could start with c of I plus 3, where c is being stored in S2 there. So for our first line of code, we would want to make sure that we are going to take that offset of I and add it to our base address of our C here. And that would be our first add instruction. Technically, once we start to load this into Mars or look at compile outputs, it's add unsigned because we're not calculating overflow. But something I had mentioned is if you don't include the U there, I don't care, and so you don't have to care right now either. Let's store the result in just some temporary register here. And we want to take the value of C and add it to whatever is corresponding to I. And at some point then we do have to specify, well, by the way, I is corresponding to something. Let's say X is going to be S3. And let's make I corresponding to S4. And let's use temporary registers for all the remainder. So we have I and we have C. We want to add I and C together to calculate that offset into memory corresponding to C of I, not the plus 3 yet. So that would be adding S4 to S2. And the order shouldn't matter there, but either way is fine. And we definitely want to add a comment there now, right? So now T1 is then corresponding to the address of C of I. And for those of you who are looking at this the first time, you may say, hold up here. You just spent all that time in class talking about how we have to do these shift left logicals to do our C of I's, because we have to calculate that times 4 value for these addresses that we're calculating. That is generally the case. It's the size of the data type that's relevant here. Our loads and stores are calculating an address in memory corresponding to this linear array of bytes, where each byte is its own +1 address in memory. In this case, we're accessing C of I, and so I is corresponding to individual bytes. Each of those are characters. Each of those are just single byte entities. Our addresses would go 1000, 1001, 1002, 1003. So you could put a shift left logical here just to make your code look very consistent and formulaic, but it would be a shift left logical of 0, right? You wouldn't be multiplying it by anything, or multiplying it by 1 is what you'd be multiplying it by. So if that helps you keep track of it, that's fine, but we don't need to do any of the shifts for this case because, and maybe we keep track of this here, C is 1 byte. Each value in C is 1 byte. And so we're just adding it together to get that new offset. We haven't actually loaded the value yet. We've calculated address of C of I. We actually need C of I plus 3. And the nice thing is that our load instruction allows us to directly encode that constant offset into it. So we'll load into T2 an offset of 3 from that address corresponding to T1, which is address of C of I. In this case, now we're saying T2 is now equal to C of I plus 3. Or J, as we labeled it in that diagram there. That was just our sort of internal temporary variable corresponding to this. Right? That we could have done a separate add immediate instruction and then done our load with a constant offset of 0. That's also perfectly valid. We could have done add immediate T1, 3 to just directly calculate the pointer as opposed to having it as part of the load instruction itself. we don't need to do that either. The load instruction allows us to directly encode the offset into the instruction itself for that exact purpose, because doing something like c of I plus 3 is just a natural thing we would want to occasionally do. Um, it's not a super important point, but we're loading bytes here, so we're not actually loading a word. We're just loading a single byte. And the architectural implications of that we will get to. You will implement that yourself at some point. We're loading a byte because it's really just that one byte of memory we want. That's a separate instruction than load word and load half word, but it's doing the same thing. It's calculating an address, it's connecting that to memory, it's loading that value back. So we're already 1/3 of the way there, right? And we have that complexity of that C statement above, but it's really just now B of J plus 4 is what we're calculating next. So we have our location of B that is stored in our place of S1 as our register. We now have J. Now when it's time to calculate B of J plus 4, because B's are these 2-byte entities, we do need to do that shift left logical. And we may want to put like, a little label here that, all this is corresponding to our J calculation here. We have J now, we need to multiply it by 2 because it is whatever was in C of I plus 3 is now part of our array index into B. We need to multiply that by 2 to get the actual offset into the base from the base address of B. So that would be a shift left logical. I'm going to use temporaries until I run out of them. We've calculated T2, and that's our J value. And we're going to shift left logical by 1. And our comment that I would put here for this one would be T3 is something that's not really shown in the C code. It's literally J times 2. We have our index into B. Because each B is a 2-byte quantity, we need to multiply that by 2 to get the actual offset here. We then need to still add that offset into B to get the result that we want. So there's still going to be an add instruction here. It doesn't go away because we're having to add that value. Let's put that in T4. Let's take that T3. And we are going to be adding that to S1. And that is now our address of B of just J, where each element of B is 2 bytes. And B is corresponding to S1, not for any reason other than we decided it did. We made that call, and so now we're using S1 as we declared it. We have calculated 2 times J. We've used that to now calculate the actual pointer into B of J. And now we're going to do a load half word, because it's 2 bytes we're loading, into yet another temporary register here. With that address we have previously calculated, plus 4, so B of J plus 4, that 4 corresponds to 4 shorts of an offset from B of J. That's going to then correspond to 8 bytes away from B of J. So we would directly encode the 8 there. Where T5 is now corresponding to B of J plus 4. And if we were to kind of just summarize this entire section here, this is now our K. Okay, we're still going well here. We now have a value K, and now all we're calculating is A of K plus 5. And so that is now the exact example we did in class. Let's still do it here. We have K, and it's stored in T5. We now need to multiply that value by 4. Or equivalent of shifting the left logical by 2. Making a note here, now T6 is storing K times 4. Because now A is corresponding to integers, and each of those are 4 bytes. We need to multiply by 4 to get our offset. We're going to do an add to get our base address added to our integer offset. Oh, you almost caught me. T7, T6, and we had put A in S0, and that's address of A of K, and I won't belabor the point, but A is are 4 bytes each. That's why it's that multiply by 4 operation we're doing here. And now finally we can do our load word, and it is a word that we're loading this time with A of K plus 5, and I designated for X, it just happens to be stored in S3. That's why we have S3 here and not another temporary. Um, A of K plus 5, each 5 is corresponding to that 4-byte quantity. That'll be an offset encoded in the instruction as 20 with our new address um, as T7 here. You can just say something as simple as, S3 is X, or S3 is, at some point, you're getting it and you just want to get it done, and I understand that as well. K plus 5, and then this whole quantity then corresponds to X. And taken together, that's what I would say is the correct mapping. There's some variance in how you can do this example. Again, as I mentioned, as opposed to using the constant offset in the load words and load bytes load instructions, we could have had another add immediate instruction before each load to just add it directly. That's fine. It's kind of wasteful. The load instruction lets us do these constant offsets within some 16-bit range here. The order of some of these things isn't super negotiable. We don't know what A of K is going to correspond to until we've calculated K, so we really do need to go from inside out. Um, and then the other thing will be, your registers, unless the problem specifically says use this register for this and use this register for that, don't worry about the registers. There is no reason other than the book sometimes does it that I'm using S registers for array addresses and T registers for temporaries. There's no deeper meaning to that other than I need some naming convention to keep track of what I'm doing here. So this is a standalone example. Please, post on general if you have any questions about this. This is the kind of thing that, it may not be super easy right now today, but this is a decent enough resource and reference that just come back to this and let me know when you have any questions. Um, and of course, let me know if I had added any bugs to this example, but it seems roughly correct. Otherwise, I look forward to seeing everyone in the next class. Thanks.